So welcome to the sixth and final talk of the Lent term. Today we have a little bit of a departure from our regular schedule. So we have Dr. Darshil Shah, a Senior Research Associate at the Center of Natural Material Innovation, which is just downstairs. And he's going to talk to us today about innovations in biomaterial engineering with an emphasis on wood, hemp, and silk. Shah obtained his PhD from the University of Nottingham, during which time he developed a wind turbine blade made out of flax biocomposite. Following which he joined the Oxford University Silk Group, where he developed a high-toughened silk-based polymer composite for defense and aerospace applications. At the center here in Cambridge, he mainly looks at engineered wood and bamboo composites for construction, as well as natural fibers for reinforcement in structural composites. The talk, as usual, will be 45 to 50 minutes, followed by a 10-minute Q&A session.
Okay. Thank you. Thank you everyone for being here. So I'm a material scientist, studied engineering in the beginning, and came to the architecture department to do continue work on plant-based materials for construction applications, but then have continued working on other bio-based biomaterials for applications in commodity products as well as automotive, transport sectors and other industries. So this will be mainly a materials talk with some discussions about their applications in construction, but also other areas. And because I'm fascinated by nature and I look at nature for inspiration, for materials, one of my key aims of the talk would be to try and get you enthused about nature as well, if you're not already. So I work in the Center for Natural Material Innovation, which is just downstairs from here. And we have quite a multidisciplinary group where we work together to solve problems about using less embodied energy materials, especially if they're plant-based, for applications in the construction sector. And we work across length scales, so with biochemists we work right at the molecular scale of actually how plants develop wood and how these plant sugars, they come together to make this beautiful material that wood is, with its brilliant properties, diverse properties. And then we look at it at the cellular scale to understand, for instance, how fluids flow in wood and how we can modify the properties of timber for better applications in construction, but also elsewhere. We also explore how, for instance, if we have ancient treasures such as the Mary Rose ship, and if we take them out of the sea, things happen to the wood, it starts to shrink, for example, and we need to preserve and conserve these things. And we need to understand how we can use chemicals and monomers and polymers in particular to make wood a durable material. And finally, at the larger scale, we look at the material properties of timber and its use in construction. So the main driver of my research, as well as the center's, is climate change, of course. And we know particularly the building and construction sectors are major contributors to greenhouse gas emissions, as well as to solid waste that is the solid waste that is delivered. So, for instance, in the UK, the built environment accounts for 45% of total carbon emissions, and the other staggering fact is 32% of landfill waste comes from the construction sector, and particularly 13% of products that are delivered to construction sites are sent directly to landfill, and these are because of wastage that occur during production. And therefore these are concerns that we ought to consider and try and solve. And from the beginning I have been interested in nature, as I've mentioned before, and one of the questions is, why do we want to learn from nature? Well, it's partly because nature often has a very different way of solving problems. And this was a very interesting, quite a long piece of research by Julian Vinson from University of Reading, who looked at how we, in terms of technology, solve problems and how nature solves problems at different length scales, as you can see from the nanometer scale to the kilometer scale. And he looked at dividing the problems into how they can be solved in terms of information, energy, time, space, structure, etc. And the key finding from that piece of work was that in terms of technology, how we solve problems, we are extremely reliant on energy. And we like to heat, beat, and treat materials to make them into certain shapes and to design solutions. Whereas biology has a very different approach. Of course, energy is the basic currency of life, and therefore nature tries to conserve that as much as possible. It also has to expend quite a bit of energy for reproduction, for instance. And what nature does is it tries to use embedded information as well as structure to bring out interesting solutions to problems. And particularly, you will find in nature very simple building blocks like sugars, which is building block for cellulose or starch, or proteins, which is a building block for many of the other natural materials that we have. For instance, skin is a proteinous material, hair is a proteinous material, it's keratin. Our bones are made from collagen as well as hydroxyapatite minerals. So again, nature uses quite simple building blocks which are easy to produce, but it structures them in hierarchical layers and uses architectured materials so that there is most efficient flow of forces, for instance. And this brings us, learning from nature brings us firstly to the realm of biomimicry and biomimetics. So this is, for instance, one method how we can look at design by looking into biology. So it's a top-down approach in which we are asked, we have a problem, and then we look to biology of how it solves it and then try and mimic it. And very commonly described option is how to look at, for instance, termite hills. And even in forest fires where the temperatures outside may be over 100 degrees or so, inside a termite mound, the temperatures are still 20, 30 degrees. And there have been some buildings that have been designed through natural ventilation and looking at passive cooling and build those sorts of designs to make energy efficient structures which use less energy. At our research, we also look at, for instance, another approach for bioinspiration is, so this is the tallest wood building in the world currently. It stands at 50 meters tall or so. It's a Trea building in Norway. And that's the tallest tree in the world, Hyperion. It's 115 meters tall, so substantially taller than the tallest wood building in the world. And one of the questions that has come up is, how do trees, such as this 115 meters tall, actually take water right up to its top? Because that's 100 meters high, so the pressure difference would be by a magnitude of 100, and it doesn't have a motor or pump. And we struggle to with some of these problems as well by trying to take water up to heights. And therefore, one of the things we have been looking at is by putting pieces of timber into a micro CT scanner and looking at in situ imbibition experiments. So basically how uptake of water occurs without pressure and with pressure, and to understand how the channels in timber actually take up water, as well as looking at the different valves that are in these tracheate channels. And through these experiments, we can get quite nice images of, we see that the water actually flows in the early and late wood interface. So the interface between the summer growth and the winter growth, where you have larger porosity channels, big lumen sections which take up nutrients and water. But this sort of research not only helps us tackle fundamental questions as to how trees transport water, but also help us realize more relevant technological questions, such as how do we best impregnate wood, so polymerize wood, so that we can modify its mechanical properties. And in this aspect, I have been looking at 4 different natural material or classes of natural materials, firstly for inspiration, but also for direct use. And first I'll briefly introduce you to these materials. So one is bamboo, which is a monocot grass, and bamboo has a beautiful hierarchical multi-layered structure, as you can see over here. Each cell wall in bamboo has over 8 layers, so that's quite a lot of layers. And recently we did some thermal microscopy studies. So this is basically at sections of 8 or 10 micron size, we put an AFM tip and we heat that tip and look at thermal conductivity differences in the different cell wall layers. And this study was partly to try and understand how we can model better the thermal transport properties of natural materials. And through that study we find that the structure of bamboo is not only you have 8 or so layers, but you have these thick and thin bands. And these thin bands they are brighter and therefore they have lower conductivity. And basically it tells us how the fiber structure is also different in the different layers. So basically in the thick layers where you have higher conductivity, the cellulose fibers are oriented along the fiber direction, and that means that's where the strength and stiffness of the material is, but also transport properties will be better in that direction, thermal transport. Whereas in the thin sections, you have lower conductivity, and that's because cellulose microfibrils are oriented basically at about 90 degrees to the fiber direction. So that sort of research can inform you about the structure of bamboo and other plant-based materials. But interestingly, we also learned as an inference that bamboo is a fast-growing, rapidly growing material. It grows at about a millimeter a minute or so. It's fairly rapid growing. And it's producing this reasonable strength material, reasonable stiffness material rapidly, and the solution it is using is to have multiple layers that are at not 90 degrees. And this is very similar to the approach we use to make plywood and cross-laminated timber. It's mainly for rapid production and reasonable properties. So it's also bio-inspired in a sense, although it may not have been directly considered when we were designing plywood, or the Mesopotamians did 3,000 years ago, or whenever that was. But you can see quite interesting connections. So bamboo is a plant-based material based on sugars, mainly cellulosic fibers. I also worked on marine worms and how they make these beautiful structures, these tubes. And they are tube-dwelling marine worms. They are Chytopterans, marine worms because of their many hairs. And they are also bioluminescent. One of the interesting things about nature is that it doesn't try to just solve one problem. It has many problems that it tackles and has a solution for all of them in that. So it's multifunctional. That's what the usual term for those sort of materials is. And it's tube dwelling, and the tube functions itself as a venturi tube, and it filter feeds from within this tube. So it pulls water from one direction and pushes it out in the other direction because it's entirely sedentary and it's entirely tube dwelling. So it cannot actually function and live outside the tube. In fact, it relies on the tube for feeding, but also it has these respiratory features, so it's actually spinning these fans to circulate oxygen in the tube, and that's how it breathes as well. So it feeds and breathes basically relying on the tube. So the tube is very important to it, basically. And if you look at the structure of the tube, again you see these hierarchical layers. You have 20 or so layers in each section, and it is fascinating to see that all the fibers seem to be very aligned. So the question arises, how does the worm actually make these tubes and ensure that it is so well aligned? But also if we do some further examination of the orientation of the fibers, we see that the worm orients the fibers in very specific directions. And if you again compare these to how composite pipes and tanks are made, these directions are the same as you get in terms of maximum shear and maximum principal stresses. So to avoid the tube from fracturing or shearing. And nature has solved that problem through a different process, probably by trial and error over several millions of years. And if you try and further look into how the marine worm makes the tube, it actually again uses the same features from its mouth to try and wrap these filaments in specific orientations. And this is very similar to how green industry made composite pipes and tanks. This is known as a continuous filament winding process. And the marine bagworms, it's a mixture between protein and sugar. So again, the same basic fundamental materials. It's a mucopolysaccharide, as it is called. The third group of material is a bio-nanocomposite mixture of organic and inorganic components. So that's elephant ivory. And I was working on that for elephant conservation, trying to make synthetic ivory. Again, it has a very hierarchical 3D structure, and I'll come to ivory a bit later on. The fascinating thing about ivory is that although it can be locked away, confiscated for instance, for decades, if you try and do the analysis on what the material composition of ivory is, you find that about 25% of it is water. So again, that's another thing that material scientists and we need to look at, how to use water to realize certain properties, and because especially water is an environmentally benign material. And we need to better use water to achieve certain functions. And we believe that water plasticizes the polymers in ivory and therefore affords it the toughness that elephant tusks need, because if two bulls are clashing onto each other, the tusk needs to be impact resistant for those sort of loads. And the fourth category of material is a proteinous material, and that's silk. So this is silkworm silk that I mainly explored. And silkworms, as many of you may know, they produce these cocoons. And each cocoon is composed of a single dual filament that is continuously wrapped around the cocoon. And if you were to unravel it, you get about 1,000, 2,000 kilometers of fiber. And it does that within 5 days or so. So you can pass these materials around or come look at them later on at the end of the talk. And it uses two primary proteins. Fibroin is what provides the strength to the fiber. Sericin is a globular protein that glues the two together. And again, if you look at the microstructure of the cocoon, it's a composite microstructure, highly non-woven. So before you saw aligned multi-axial materials, and these are non-woven. Partly because silkworm cocoons need to be resistant to peaks from birds so that they are not eaten, and therefore the non-woven structure gives it better penetration resistance. So again, it's nature trying to use structure to achieve certain functions. And then more recently, we've been trying to recreate synthetic silk, and we've done that in collaboration with the chemistry department, taking two fundamental materials. We took silica, which is basically sand, and modified it with some polymers, and used hydroxyethyl cellulose, which is again a cellulose derivative, a sugar derivative, and we mixed them together using a very special molecule called cubituril, which is donut shaped. And what this molecule does is it makes the first two polymers or molecules hold hands, so it handcuffs them together, and it has to be in that fashion. It makes it self-assembling, so that it's only these two that are handcuffing together and not one cellulose molecule with another cellulose molecule. And when you mix them, you can form these highly elastic hydrogels and fibrous materials. And again, if you look at them under SEM and a transmission electron microscope, you can see the multiple length scales and the hierarchical structure in that as well. The other aspect of this was it's a hydrogel, so it's 98% water. So again, trying to use water as a fundamental material to make materials. Again, when you look at spider silk, the spider is spinning these fibers, which are really tough and really strong, using water as a solvent at ambient conditions, whereas when we are making polymer fibers, they're not biodegradable usually, and we require 200, 400 degrees Celsius to actually melt them and then spin them. So again, this is trying to use ambient processing and using water and benign organic solvents to produce useful materials. So we can make synthetic spider silks, but we can also use the silks that we have, like cocoons for instance, which are then converted into fabrics. So we can use these as reinforcements in polymers. And that then we enter the realm of a composite material. So a composite material, which many of you know, is a heterogeneous material. It's a combination of usually a matrix, for instance a polymer, a plastic, and some fibrous materials. So it could be glass fiber, carbon fiber, it could be sand, and it could be natural fiber as well. And a lot of us would know about biocomposites. Generally, wood is a natural biocomposite material because the cellulose fibrils are the fibers, and the lignin, for instance, is a matrix material. But there are quite a few different terminologies which can sometimes be confusing, but in general, a biocomposite is when at least one of the components is natural or bio-based. And we have used biocomposites for a long time. In fact, the first composites were biocomposites. So as I mentioned, the Mesopotamians creating plywood because of a shortage of high quality wood, so they took very thin slivers, glued them together to create a more homogeneous material with homogeneous properties. In 2,000 years ago, the Egyptians and so on were using linen and papyrus and soaking them in plaster to make to wrap them around mummies. So that's a composite material as well. We have straw, rice husk reinforced mud bricks, which are still used today. So this is mud brick buildings, high rises in Yemen, 30 meters tall. They're over 500 years old and still standing. So you can have natural materials that are very durable as well. So for silk composites, we primarily explored two routes. First, we looked at making syntactic foams from them. Foams are a very important class of materials. We find them everywhere in the soles of our shoes, in insulation, for instance, in mattresses and bedding, and you get very different classes of foams as well. There are diverse properties. And what we did is used recycled vegetable oils to make the matrix and reinforced it with the cocoons that you saw previously. And the cocoons provide structural resistance, and the foam provides the ability to form it into certain shapes. And the foam, however, is often more environmentally polluting because it's oil derivative. In our case, it was vegetable oil, but only 30% of it was vegetable oil. It's quite difficult to get 100% bio-based matrix polymers. And we were using exactly the silk to give strength, and these are fairly high compression strength resistant materials. So if I stand on it, it does not compress substantially, and in fact, that's how materials like honeycomb structures came about. The honeycomb paper structures came about from the circus industry, where they needed a material where an elephant could stand on, for instance, and not swim. The other form of material was these silk composites, in which we have these textile fabrics, and you put them in a polymer or resin, and then form these stiff materials. Again, I'll pass these around. The other thing we looked at was, well, we have these cocoons, and to make silk textiles, what we do is we put these cocoons into boiling water, usually at 95 degrees C, and we reel the silk out by taking the glue out, the sericin. And in the process, obviously, we kill the worm. And then we reel the fabric, reel the fiber, we spin it and spool it, and then after that we weave it into certain structures. And it's quite an energy-intensive process. So silk production itself is quite energy-intensive, and I'll go into that later on. But we thought, why don't we use the marvelous non-woven structure that nature has created and make composites out of it using that non-woven structure. So what we did is we take the silkworm, the pupa out from the cocoon, so you can hear the pupa inside it. And so you chop one of the ends out, take the pupa out, and then if you are to spray some water onto these cocoons, and just using a trouser press at 140 degrees C, compress it, you can get mats like these. And then you can impregnate these mats, non-woven mats, with a resin and form a non-woven composite. And that's what we looked at. So with the cocoons themselves, we found that the cocoon-reinforced foams were substantially better in terms of their mechanical properties than polymer foams themselves, because the cocoons are providing structural resistance. But using the cocoons, we are also replacing about 40 to 70% by volume, 60 to 90% by weight of the polymer itself. And the polymer has an embodied energy, so how much energy goes into the polymer of about 140 megajoules per kilogram. So replacing quite a lot of it with just air. So that is an environmentally beneficial thing to do, at least we thought. And then I'm going to the LCA, the life cycle assessment of silk itself later on. For the composite mats, we found that woven silk and non-woven silk composites had very interesting properties, and what put them apart in comparison to glass fiber composites and linen composites, flax fiber composites, was their high stretchability. And obviously that's what silk is known for. Often silk is thought to be tough enough to stop bullets, and that's why there is often a myth that silk vests can be used for bulletproof vests. But I often say that's not entirely true. A silk vest will stop a bullet, but only when the bullet is a meter or so behind you, by when it's not much use. And that's because of how the properties of silk come about. It is very strong, but it also stretches in the process, and therefore That's what gives its toughness. And you observe that in silk composites as well. So it's the impact strength and the high flexibility, the high extensibility of silk composites that is interesting. And we therefore consider them for applications in the aerospace sector and for defense applications. So the work I did at the Oxford Silk Group was funded by the US Air Force Research Laboratory. And it was for defense applications, but very fundamentally. So we did some bullet impact tests on different materials. So this is on, oops. So that was a glass fiber composite. So if you put a bullet at it at about, so metal ball bearing at it at about 150 meters per second, you see these fibers delaminating from the structure and fiber fraying, which is what you'd observe in typical glass fiber composite. And that's why it's a bad idea to use glass fiber composites in places where impact resistance is required. Glass fibers can cause irritation as well, but also there are health and safety concerns. So we looked at the behavior of silk fiber composites when you put a bullet to it, and you do not see the same fiber delamination or fraying as you do in a glass fiber composite. In fact, you see that there is some, so it absorbs energy by some form of deformation, and that deformation can be viscoelastic, okay, so that it can recover to an extent as time goes by. And we also looked at the bullet impact properties of ivory, because again, its relevance for impact strength. And you see a very similar performance. You do not see any fracture or fraying, so you do not see cracks growing, for instance, and that's at a bullet impacting the ivory structure at 150 meters per second. So that's also very interesting. While we would consider ivory to be a very brittle material, and it would break quite, or at least form cracks very readily, often nature, using the hierarchical structures, has methods to stop crack propagation and deviate cracks into micro cracks so that it's absorbing more energy. And that's what we have been trying to recreate. And as I mentioned earlier, it's quite relevant for elephants themselves, because they need to, if it's a bull, for instance, they might be coming towards each other at 30 miles per hour and then using their 2-ton heads bumping tusks into each other, so that's a lot of force. With the silk composites themselves, we made some helicopter pilot crash helmets, looked at their properties, and we find that, again, most of these natural fibers are quite light. They have a density of around 1.4 to 1.5 grams per centimeter cubed. In comparison to glass fiber is about 2.6 grams per centimeter cubed. So it provides 50% lower densities, and therefore in a composite it would be about 30% lower, so that's what we observe. What silks and other natural materials also afford, because of their polymerous structures, is the ability to functionalize them, attach sensors onto them, chemical sensors at least. So one of the things we looked at was you take a piece of silk and you attach a mechanophore dye to a piece of silk, and then you attach that to the resin. So what you have is the fiber, the silk fiber, and the resin being connected by the mechanophore dye. And what we mean by mechanophore is something that lights up or changes color when force is applied to it, or strain is applied to it. It's also a hydrophore, so it can sense how much water there is as well. And what you do is, once you load it, you can see a change in the excitation wavelength and can see it coloring up. And this is very interesting for applications in where you want to sense and monitor strains and stresses in structures which are difficult to test otherwise or non-destructively. So for instance, if you have an airplane wing which you do not want to periodically break apart of and then test, these sort of mechanophore dyes and other chromophores can help you analyze and monitor how damage is propagating or evolving over time. Finally, about silk production, the reason I put this slide in here is to mention and highlight that just because a material is natural does not necessarily mean that it is going to be environmentally friendly for a particular application, and that life cycle assessment or some form of fair assessment method is required to fairly proclaim whether something is environmentally friendly or not. So the Chinese bred silkworms over 5,000 years, and they have bred these silkworms into producing these beautiful white cocoons so that they're easy to dye. That's one of the key criteria, but also the cross-section shape of a silk fiber has evolved. So now cross-section shapes of silk fibers are fairly triangular, and that's why it is a very shiny, and that's what provides the luster and sheen of silk, because it refracts light in specific orientations, whereas spider silk is circular in cross-section. So that's a very distinct difference between spider silk and silkworm silk. But also, if you look at a wild silkworm cocoon, it's much wilder. It has calcium oxalate crystals on top. It's not white and lustrous because it doesn't serve the evolutionary purpose of trying to protect itself from birds trying to eat the pupine grubs. And in silk production, what we do is we use high energy practices. We boil these in water, and usually these are subsidized farming sectors where they use as much wood as they would like. So it's about 25 kilograms of wood for 1 kg of silk, which is quite a lot, and that's just trying to boil water which has a high CP. And silk production is also a two-step industry. So to grow the grubs, you first have to grow the food that they like, because they are fussy eaters. They only have mulberry leaves, so you need to grow mulberry plants. And then you take the leaves from the plants and feed them to the silkworm so that it can form these silkworm cocoons. And therefore you need to take into account the energy that goes into growing the mulberry plants in the first place. And those two aspects make silk itself a very high energy fiber. In fact, it takes about 1,000 megajoules per kilogram to make silk. And if you compare that to cotton, which is the other most polluting fiber, that's about 140 megajoules per kilogram. In comparison, hemp requires about 15 megajoules per kilogram, and that's for the final yarn that you would get, so after spinning and decortification processes. So plant fibers in that respect, especially if they are from a waste sector, are much more environmentally friendly in terms of their embodied energy. So I work on quite a few plant fiber composite materials. More recently, we have been working with hemp that has been grown in Cambridgeshire. So this is part of a Margin Farm, who have a 53-acre farm in Pidley. Grow 3 varieties of hemp. One is for growing seeds for oils, for medicinal purposes. The other is for growing larger stalks with big diameters for their ships, for making hempcrete, for instance, for building applications. And the third variety is to extract high quality fibers, and that's for the textile sector and the composite sector. So different varieties will have different purposes, and these have been bred for over hundreds of years. In fact, we started using plant fibers 45,000 years ago. So there was a study in 2012 in Nature or Science, I can't remember which one now, which found that we had started to use wild flax fibers for clothing and other applications, basically trying to make knots and stuff to put weapons on, I suppose. And that was about 45,000 years ago. So we've been using these plant fibers for a long time. It's only more recently that we've explored them for composite applications. So Steve also uses hemp for hempcrete applications, and in the farm he has built a couple of buildings with hempcrete. I'm sure so the purpose of that facility is it's a working lab, it's a research lab, so when it's up and running, I think we would all be welcome to go there and visit and see the site itself and see the hemp growing, for instance. And I'll try and organize a trip or something like that in the near future, possibly around May or June. Steve Barron, who owns Margin Farm, he's a film and TV director, producer. So we started working on first trying to create a camera casing, replacing carbon fiber composites with hemp fiber composites. And in this case, we were using completely bio-based polymer, polylactic acid, PLA, which is derived from corn sugars. So it's bio-based and biodegradable. So the idea is that you can compost the cases and then replace them if you need to, but you can also recycle them because PLA is a thermoplastic, so if you were to heat it, it melts and then you can reprocess it. So that's the idea. We have been trying to look into the technology of laser cutting these materials, etching them, and also moving away from pigmenting the matrix itself and rather using natural dyes for the fabric to give different colors and textures, and that's quite new for this industry. So here you can see the different coarse weave structures of hemp, but in reality it's the top woven layer is just for appearance. Much of it inside is a non-woven hemp structure, so we are just using that to fill it. So that's a very low-cost material. So that's just a process segment of that. It's hot compression unit. But apart from these applications where structural requirements are not present, my main focus is for structural applications. And I've been looking at using hemp and flax, linen for instance, in composite materials for applications such as in wind turbine blades, but also in automotive components. And for plant materials, you need to consider a lot of factors. So from the agronomics of growing the plant, what conditions are best for it, which variety is best for it, that can have a big influence on the properties of the actual fiber. Also, I should mention that the variety that is used for sheaves or for growing fibers is not the same as the one that is grown from marijuana. Obviously, they have different THC contents and therefore they're not suitable for that application. And in fact, industrial hemp is a big industry in itself, especially in Canada, but also in Europe. And it used to be in Britain a while back. So this is, for example, a slide of when plant fiber composites were actually being considered for alternatives in engineering applications. So this is Henry Ford taking the sledgehammer to the Ford green car that he was trying to develop, which was based on lignocellulosic fibers, mainly from hemp and flax and rainy, about 70% of fibers, with a soybean oil-based matrix. So again, using green composite materials for his car. It didn't go into production because soon after that, oil prices dropped because of oil reserves becoming available, but also the US banned hemp soon after, and there was the World War as well. So it stopped that industry growing much further. And in fact, the first synthetic composite materials and polymers that we were developing were mainly natural or bio-based, bio-inspired at least. So viscose was the first synthetic polymer fiber that we started to develop. A lot of bamboo fiber that goes about in the market is actually bamboo viscose. It's not really bamboo fiber. They regenerate bamboo into cellulose and then they make it into a fiber. So it's just a marketing gimmick in some places. The other is Gordon Aerolite, which was developed not far from here. It's in Duxford, so a few miles from here, where they have the Aero Research Laboratory. And again, during the Second World War, there were potential shortages of bauxite, which is an old resource for aluminum in France. And so they were looking at alternatives for aluminum for the military sector, and they were considering flax phenolic composites, and they found that it was a potential alternative material to aluminum, and aluminum is a lightweight metal. So again, the potential of using natural materials for lightweighting is a big one. And in fact today, if you look at the biocomposite industry, it's about 13% by volume globally as well as in Europe. A lot of it are used in the construction sector for decking. Otherwise, it's for the automotive sector. So BMW, Audi, all of these car manufacturers utilize natural fibers for instrumental panel, dashboards, things like that, for lightweighting purposes as part of meeting government legislation for recyclability and reusability of car components. Yeah, so these are the main markets for natural fibers. What I find fascinating is people in the composites world find natural fibers to be new materials, but natural fiber composites are a substantially larger market than carbon fiber composites. Carbon fiber composites are only 2% of the fiber reinforced composites market. And yet if you go to a composite conference, it's mainly carbon fiber that is discussed, although biocomposites are upcoming. There are quite a few other plant fiber composite applications, but these are one-off products. In fact, the Victoria and Albert Museum currently has a section right now on design by nature or something to that respect, where some flax composite products are in display. What I focused on was firstly looking at their applications in wind turbines, because wind turbines are model engineering components. They have to endure static loads, and if you look at wind turbine testing standards, they have to endure hurricane wind speed loads, which is 59.5 meters per second, so it's quite fast. And they also have to endure fatigue loads. So over its design life of 20 or 30 years, a blade will be rotating 10 to the power of 9 cycles, and fatigue, so how the properties develop even at small loads over a function of time, have a deteriorative effect on the material. So if you think about, maybe it's just me who does it, but if you have a paper clip, it's quite difficult to break a paper clip by itself, but if you were to flex it up and down a couple of times, soon after it starts to yield. And that's at loads much below the forces that it would break in under static tensile loads. And fatigue load does exactly that. Even small loads, but done cyclically over periods of time, make the material or structure break at much lower loads than they would in monotonic stress conditions. And that's why a wind turbine blade is a good example of that. So first off, I started by looking at which fiber we should use. And there are lots of plant fibers that are available to us. And if you were to plot them on a graph in terms of their different properties, so this is strength against their stiffness. Stiffness is the ability for it to resist deformation, so deflection. We find that bast fibers, so fibers that have evolved to give the stem structural support, such as flax and hemp, they are the ones that would be more suitable for applications where stiffness and strength are required. Seed fibers, obviously, they do not have any evolutionary reason to have to resist certain strength or stiffness requirements, and therefore they do not have those properties and would not be suitable. Although in terms of their cost, that would be useful. Then we look at which type of preform we want to use. So in composite, you have to choose or even make your own preform. And a preform is basically the form of your reinforcement material. It can be short fibers, which is what you use in 3D printing, for instance. It's basically flour that is less than 100 micron in size. It can be non-woven mats, as you saw previously, so shorter fibers. But you can also make aligned textiles. These are, for instance, biaxial and a unidirectional mat. So these are long fibers in very specific orientations. And these give maximum properties in those orientations. And from that, we made these composite materials. And we made a design for a wind turbine blade. So this is where the foam is. You have skin caps, and in the skin caps, the fibers are oriented at plus minus 45 degrees, and in the red section, which is the blister cap, fibers are oriented basically along the blade length to resist axial loads, flexural loads, basically. And we made a flax composite blade and a glass fiber composite blade using very similar processes. And from the analysis, we firstly saw a flax blade was much lighter, and lightness can be very beneficial, as I mentioned earlier. In a car, it improves fuel efficiency over periods, as well as in aerospace applications. And in wind turbine blades, it reduces the loads that a turbine is facing, because the rotational load, the centrifugal load is m omega squared, so mass is proportional to the centrifugal load, and if therefore mass is reduced by 10%, the flexural, the centrifugal load is reduced by 10%. And then we tested the blades to specific wind turbine standards, and we found that both of the blades survived the required testing standards and demonstrated that a flax composite could be used for structural applications. But we also observed that behaviors were quite different. So most synthetic fibers have a very linear behavior in terms of how strength and deflection are related, the tip displacement and the load. Whereas natural fibers and most natural materials tend to have non-linear behaviors. And this gives rise to design challenges, because most of our design standards are based on synthetic materials, and therefore there are clauses that mean you cannot use materials which have non-linear behaviors. For instance, if stiffness deteriorates by 5%, then you have structural failure. In a flax blade, the stiffness evolves as a function of strain, and therefore it changes by up to 30%. And basically it means that either we need new design standards for natural materials, or we need to design blades differently for natural materials, and we cannot use the same design. So previously we were using this sort of design. We may have to have graded structures across the blade so that it can meet the testing standards. And what it means is, effectively, if you're using natural materials, you may have to rethink the design as well. You cannot use natural materials just as drop-in solutions all the time. You may have to redesign the whole thing. There are also construction applications. Obviously, I haven't done that yet. This is the one by TU Delft and Eindhoven University, where they have looked at making biocomposite bridges, and this was actually a student project, the 4TU Light project, in which about 40 students got together and examined different natural materials, including flax composites and foams and things like that. And they made a 14-meter bridge, which is now the world's largest biocomposite bridge. It weighs 1.4 tons, which is 4 times less than what would be conventional if it was made from other materials, like concrete, for instance. And developing on from that, in Netherlands, they are now building a cycle and footbridge 60 meters in length using biocomposite materials as well. And 80% of the composite will be, of the deck will be natural materials. We have also recently started a project called Flower, in which we are looking at flax composites for boating applications, so making sailboats, as well as automotive components and point-of-sale sector advertising panels which are biodegradable. So different functional requirements using basically the same materials. Going into timber quite quickly, just looking how much time I have. The global timber market is substantially larger than the composite market. So composites are 2.4 million tons. We produce about 2.2 billion tons of timber itself. So it's 3 orders of magnitude larger. But if you look at a global analysis, we find that 54% of the wood we use is actually used for fuel rather than for construction or for other purposes. In fact, only about 30 to 40% of wood is industrial round wood, and that goes in to use for construction. And therefore there is a huge potential to use more wood for applications where we can lock in the carbon for longer rather than use it for fuel wood where we are just incinerating it. The other question we are often asked is, should we actually harvest forests, and is that good for the forest? Firstly, although overall deforestation is a big problem, globally we're also afforesting quite a lot. In fact, the forest size of Europe has grown by the same area as Portugal in the past 30 years or so. So forest sizes in Europe, for instance, North America as well, they're increasing, and therefore we should be cultivating more of it, although not virgin forests, planted forests. But also, what is important to realize is that trees lock in carbon when they are growing, so when there is secondary growth. And after about 100 years or so, when a tree has reached 50 to 100 years, when a tree has reached maturity and reached the size it's always going to remain at, after that there is not much net uptake of carbon because of emissions from the soil, for instance, decomposition of the soil, as well as leaves that are falling down, and the growth of new growth, for instance. And therefore it makes much more sense to harvest the wood and then let, again, carbon be converted into material, into mass. And therefore it makes a lot of sense to actually harvest planted forests. We produce quite a range of wood products, from cross-laminated timber to laminated veneer timber and glue-laminated timber, and all of these have specific properties that could be interesting for construction applications and maybe more suitable based on the energy efficiency, but also what stiffness and strength requirements they meet. We've been exploring also what the life cycle costs of wood harvesting is, and wood production, engineered wood product production is, and we find that, and these are based on literature studies, that a lot of energy actually just goes into kiln drying of wood. So 90% of energy in wood production goes into kiln drying, and that's an area that needs to be explored into how we can evacuate moisture from wood readily. But it also makes us realize that we are using wood in a way that it is not being meant to be used as. Wood in nature is always wet, whereas we want to use it dry, and therefore we need to realize that if we are trying to meet certain requirements, we may have to redesign how we use the wood in that aspect. And finally, there are lots of structural benefits of timber. Obviously, the strength to weight ratio is a huge benefit, making it possible to build lighter buildings. So with wood, you can build a building that is a third or fourth lighter than a concrete building, for instance, and that means you need smaller foundations. You can build on top of existing foundations and add stories to it. And because of the modular construction, prefabricated nature of wood construction, you can also build faster and much faster. And you can prefabricate off-site and therefore reduce construction times. And Michael and the rest of the team has been working quite a lot on the concept designs and engineering designs of timber structures. So this is one of the Oakwood Tower buildings in London that they proposed a couple of years ago. And we are trying to push the boundaries further by redesigning natural materials for engineering applications. And I would like to thank a lot of my colleagues, especially in the Center for Natural Material Innovation, but also outside of the Center for Natural Material Innovation, who we have worked together on a number of these projects. Thank you.
Thank you very much for the interesting talk. I think we can straight away jump into questions.
Can I have a quick question about the water in the tusks? Is that existing as water as we normally see it, or as molecules, as part of the chemical like in concrete?
Yes, so that's a good question. So usually water exists as either free water or bound water. And if you look at elephant tusks, so 25% is water and 11% is free water. So if you were to put it into an oven and dry it at 100 degrees C, after a period of 24 hours, weight would reduce by 11%. But the remaining 15% is actually bound, so it's actually within, stuck between other molecules, so it's bound water.
And the other question is to do with Henry Ford, because if it's 14 times stronger, they could sell it to Washington DC, right? So presidential beasts could be built with that material. So what happened to that material? What are the fatal flaws of this material at the time?
I'm not entirely sure. I think partly that was a gimmick to do with strength and stiffness as well. Strength and weight as well, so it might be using much thicker sections. That could be a possibility.
Right.
But also, I'm not sure if they did longer term studies on the material, for instance, how it reacts with moisture, and sometimes they have to undergo quite rigorous testing in terms of, for instance, do the properties remain constant at temperature? So what they do in the automotive industry is stick these in at 100 degrees C for 7 days and see if the stiffness or strength has changed, but also with humidity and ranging it from 100 to 6%. One of the other big factors that has limited the applications of natural fiber composites in the automotive industry is odor emissions. So natural fibers naturally emit odor. And in a car, regulations limited to certain limits of, I think, 5 grams per something. And sometimes it's difficult to meet those odor emission targets. So it's probably a mixture of durability and issues, smaller issues like odor.
Yeah, if I may. Thank you. Excellently. I really enjoyed it. Thank you. I just wondered if the to digress, where graphene sits in with this sort of material we hear a lot about, something I know very little. Just wondered if it sits in this sort of area or not so.
No, so graphene does not sit in this area. Graphene is a very carbonous material. However, So we have worked on graphene before and trying to use it as a coating in wood for fire resistance or fire retardants. Although our initial studies suggested that because of so graphene is quite an expensive material, and if it were to use as a coating, it needs to be in a solution of some sort, and we were mainly using polymer solutions to apply it on wood, for instance. And our observations, our fire tests found that if we had the graphene polymer coating, the timber was burning a magnitude faster in terms of time to ignition. So the reverse of what we were expecting, but it's likely to do with the polymer that we were using. And therefore we need to look at that again. But otherwise, no, so graphene does not sit into this category. No.
Anyone else? Could I ask a question about biomaterials? I mean, you looked at like things like silk and tusks. Have you come across any condition where you've noticed adaptation, where the organism is sort of changing the structure?
Mm-hmm. So adaptation can be structural. So in terms of not that the animal wants to do it, but it has built a structure itself that leads to that function. So an example would be pine cones, for instance. And if you were to put pine cone in water, it starts to behave in a certain way, but if you were to dry it, they open up. And that's how seeds are dispersed. And this is passive in the sense it's built into how cellulose fibrils are oriented in the structure, and therefore if it heats up, the cellulose fibrils dry, and therefore it makes the cone expand. So that's some form of adaptation structurally, but you can also, and then it can be passive and active as well. So an example again with wood would be the formation of reactive wood or reaction wood, and that's a big problem in industry. So what happens is when a tree grows, and if it is growing at a certain angle, at a tilt, one side of the wood will be facing more of the loads than the other, and therefore it grows reaction wood, which can be either tension wood or compression wood, based on if it's a hardwood tree or a softwood tree. And it is doing that because it knows the load parts will be quite different. So that's active, passive. And in fact, morphogenesis and how properties evolve and adapt over time is a big field, not only in plant sciences, but also biological materials as well. But you can also have active changing of properties. So examples of that would be, for instance, the skin of cuttlefish and how they are able to change color and texture structurally, and that's just because of how the cells, they basically change the shapes of the cells, and that is also possible. So it is possible with natural materials, yes.
What about climate change adaptation? Have we come across any situation where the organism has specifically altered its structure?
That's putting me on the spot. I'll have to think of that a bit. As a result of climate change, yeah, I'm not entirely sure yet. I'll have to do a bit of thinking, and I'll have to get back to you on that.
Okay.
Thank you.
Anyone else? Okay, I think that's all the time we have today. Thank you again, Dr. Shah, for coming today.